Ladies and gentlemen, good afternoon. Welcome to the webinar hosted by Solarplaza. Also welcome if you are listening to this at a later moment and you have downloaded the recordings. The title of the webinar of today is Risk Mitigation, special focus on inverters and components. My name is Konstantinos Zanakakis and I'm a project manager at Solarplaza. Brief agenda for today. First, we're going to have a short introduction on the webinar and the panelists. Shortly after, Francesc Filiberto, co-founder and managing partner of Siconia, will analyze the major inverter risks, issues related to inverter service coverage and maintenance, and also showcase different scenarios of long-term inverter service strategies. Afterwards, Olivier Haldi, business developer of Stäubli, will attempt to raise the awareness regarding one of the highest risks in a PV plant, failures on cabling and components. He will also talk about the impact that these components have on the efficiency and economical success of a PV project. Both, of course, will address ways to mitigate these risks and maximize the return of your assets. Afterwards, there will be still time for Q&A, and we will end after approximately 1 hour. So once again, my name is Konstantinos, project manager at Solarplaza. I work on the solar asset management conferences in Europe and USA, and these are my contact details. So feel free to get in touch with me if you have any questions regarding solar asset management and our conferences. For those of you that don't know Solarplaza that well, we are a global information platform for solar PV. Our main business is organizing high-level B2B conferences and trade missions, and we have organized over 90 in the last 13 years, and in more than 30 countries. We have a network of over 60,000 solar professionals and growing every day. This webinar is a pre-call to our yearly conference, Solar Asset Management Europe, and actually this year this is going to be our 100th event organized by Solarplaza. This is the 5th edition of this conference held in Milan, and it's taking place on the 7th and 8th of November. It is Europe's leading conference dedicated to the optimization of the operational phase of PV plants and portfolios. More than 350 attendees will be representing the whole value chain from service provider to asset management and investor. There's going to be leading experts on stage sharing their vision, expertise, and experience. And of course, a lot of our sponsors and exhibitors profiling themselves and their leading products or services. During this conference, we're going to cover O&M topics, financial, technical asset management, market trends, innovative technologies, PPAs, market parity projects, electricity markets, storage, and cybersecurity. And so far, these are the companies that are involved in our, this is only a selection of the companies involved in our conference at this moment. So please don't miss a chance to meet the professional of all these companies at the conference. Of course, special thanks to our sponsors, including Stäubli and Siconia, for making our conference and content possible. If you haven't registered yet for our conference in Milan, today we are providing a discount. You can use the code webinar10 on our website, and the first 10 registrations will get a 10% discount on the conference ticket. Just before we start, some practical notes. If you have any technical issues during the webinar, please use the chat box. Also for Q&A, you can also do the same. We will address as many questions as possible during this webinar. It's going to happen after the presentations finish. And the presentation slides and the video recordings will be available afterwards at our website, www.solarassetmanagementeu.com. So our first speaker is Francesc Filiberto, co-founder and managing partner at Siconia. He created a consultancy in Barcelona in 2015. He previously worked for SMA in different roles, such as Head Service Sales Europe and Director of Service Operation Iberica. And yeah, he started in the solar industry in 2006 when he founded his first project management company. Francesc, I will start with you today. I will make you a presenter right now. and you can start. Francesc, are you with us?
Yes. Can you hear me?
Yes. Good afternoon.
Okay. Good afternoon, everybody, and welcome to this webinar on risk mitigation. First, I want to thank you, Solarplaza team, for the invitation and the organization of this webinar. And for the next minutes, I will speak about the inverter risk and how to mitigate them in a long-term strategy. First, a little bit about Siconia. Siconia is founded in 2015 in Barcelona, and we are an independent engineering consultancy. Our team has more than a decade in experience in this field. We have the capability to work at every phase of the project, from development to operations. And in the operations phase, especially our focus today, we help investors to define and implement long-term strategies. So risk assessment, restructuring of service contracts, inspection, operation audits, trainings, and service negotiation. I'd like to start with a poll question that we have from our colleagues in Solarplaza. Konstantinos, can you put the poll question now?
Yes, 1 second, and yeah, here you go. Can you see it, Francesc? The poll question? Yeah, you cannot, but it's on the screen of everyone. So
okay, not mine. Okay.
The question is, what is the percentage of the inverter costs in the overall O&M budget during a solar plant lifetime? So yeah, please select one, and we will be closing soon the poll. All right. So let's see the results to your question. All right, so Francesc, just for you to know, we have 25% of the people believe that the answer is 10, 36% believe that it's 25, 29% believe 33, and 11% 50%. So yeah, okay. It's quite close actually.
Interesting. Okay, do I have the control of the window again?
Give me a second. Yes, we're back at you.
Okay. So let me start by sharing some data from several reports to show the relevance of inverter in a solar plant. Then you will have the answer to your question in the poll as well. So inverters are accountable for 60% of the events in a PV plant. This relates to number of events. Inverters are also responsible for 37% of the energy losses. And the question that we made, inverters associated costs represent 1/3 of the total O&M budget. So we could say that the inverter is one of the biggest source of risk and one of the most important parts of the O&M budget. Let's start with the risk, and later we will analyze the costs. In a solar plant, we can find plenty of risks. So force majeure, obsolescence, financial, commercial, policy changes, a lot of them. In fact, consulting company Clarion, in a recent study, identified more than 15 different major risks in a solar plant. But today, I'd like to show you the risk from a different perspective. It's called layers of protection. The most important level of protection for the owner is the EPC/O&M contract. In this contract, all the risks associated with the construction and operations are covered. For example, interconnection, workmanship, and production, performance ratio and availability related to the production. In a second layer, we would find the major equipment warranties, especially the inverters, covering the major risk associated with them. Massive breakdown, reaction times, and obsolescence. In a few minutes, we will analyze this inverter risk in more detail. And finally, we have the insurance layer that takes care of force majeure risks such as fire, theft, vandalism, and weather damage. Here it's important to understand that these three layers are at different levels, and we cannot cover the three of them with the same contract or the same service supplier. So we cannot ask the O&M contract to cover the force majeure risk, or we cannot expect that insurance or O&M contract covers the inverter obsolescence. Each layer has its meaning and cannot be ignored. Let's focus now more specifically on the inverter risk. I will use a matrix to explain this risk. This matrix has two primary dimensions, impact and probability. To simplify the analysis, inside the impact dimension, we will include both impact on costs and impact on income losses. The first risk is the massive breakdown. This risk is linked to the inverter quality. It could be caused by a failure on the component's technology, inadequate design, or manufacturing problem. And this risk is covered by the manufacturer warranty during the first years, but after this period, this risk is totally transferred to the owner or investor. The second one is the risk of delays on fixing the failures and production losses associated. This risk is directly linked to the quality of the manufacturer service. The inverter manufacturer could have a strong service structure in the country, or maybe only a small service partner without full technical training or access to components. And this will impact the downtimes dramatically when an inverter repair is needed. The third and most important risk for the inverters is the obsolescence. This is the inability of the manufacturer to repair the inverter after a failure and keep it performing as the day one of operations. These problems are being caused mainly due to the lack of components and spare parts inventory. Some years after an inverter model has been discontinued, the manufacturer could struggle to get the same or compatible components from the suppliers. And a component redesign most of the times is not performed because the inverter manufacturer is focusing on R&D teams in new technologies in old products. Now, it depends very much how the risk profile of the plant owner is, but the general recommendation for risk management is to accept the low-level risk. In this case, we have none. Mitigate or control the medium-level risk, such as massive breakdown or reaction time. And finally, reduce, avoid, or even transfer the critical risks, such as the obsolescence. Okay, let's see the risk mitigation strategies in more detail. The first option to deal with the major inverter risk would be a reserve account. There's a reserve account that builds a cash balance sufficient to cover all the inverter services expenses, such as initial stock, repair out of warranty, and eventually a new inverter replacement. In this case, the owner or investor is accepting all major inverter risk. Another option, option B, is a long-term contract with the inverter manufacturer. This contract is based in a service agreement, usually with yearly fixed cost over the lifetime of the asset, usually 20 or 20 years or 25 years, depending on the country. In this second option, the major inverter risk, especially the obsolescence, are transferred to the inverter manufacturer and they don't need to be accrued in the investor accounts. Okay, let's see how to estimate this inverter reserve account. We'll analyze all the costs associated to an inverter over 20 years. For calculations, we will use a standard solar plant of 10 megawatts AC, a peak power of 12 DC. There will be 10 central inverters of 1 megawatt located in Western Europe, UK, France, Germany, Italy, or Spain, and it will be a technology from a Tier 1 manufacturer, SMA, but it could be ABB, Schneider Electric, or Power Electronics. It's important to explain the numbers shown in this presentation are based in our experience and not in any way a market study. For a different solar system, you would need to evaluate and analyze them again. The first item that we have is the on-site stock that we need to guarantee delivery times of a spare part. This is needed because in this scenario, the solar plant doesn't have any service contract with the inverter manufacturer, and supply of spare parts is not guaranteed. So this is based on manufacturer recommended spare part list, and the cost estimation is 4,000 euros per megawatt. Then we have repair costs. Once the inverter is out of warranty, usually in year 6, the owner has to pay for the repair cost. In our scenario, we consider one minor repair per year and one major repair every 2-3 years. So the cost estimation here is 1.3K for the first 5 years and 1,000 euros for the second period. That is expected to be a little bit lower. On year 11, approximately, we will need to consider the replacement of the inverter. Remember, we have no service contract with the manufacturer. The inverter is probably obsolete by that time, and some spare parts would have become much more expensive and even not available in the market anymore. So repair at some point won't be an option. Okay. For the new inverter, we will need also to consider the replacement cost. We will see a detail of this in the following slide. And of course, a new stock to guarantee delivery time of spare parts. In total, we have an estimation of 47,000 euros for the overall inverter cost over 20 years of planned lifetime. Again, this is an exercise for a specific case, and it must be adapted in different scenarios. Let's go a little bit deeper into the details of the inverter replacement. This is something that our team at Siconia has some experience. We've done several projects like this. And here is the list of all the costs associated with the replacement. So design and engineering works, admin and legal permits, transport costs, recabling, DC and AC, civil works, commissioning and communications. And finally, let me mention something that is not in this breakdown of cost, and especially we couldn't estimate this in euros, that is production losses and cost of opportunity. Focusing your team in this task and not in the next investment will create some cost of opportunity, and this is important to consider too. Okay, once we have the cost needed to set up the reserve account, there are different ways to implement it. The most used is to save 10% of the total cost during the first 10 years. Another option shown here has a different time distribution and is also valid as well. In any case, we have to have the cash in the bank account after 10 or 12 years. To be able to compare the costs with a service contract, we need to calculate not only the total cost, but also the net present value. We use a discount rate of 5%. When you do this exercise, we recommend that you use your discount rate. Now that we've seen how to estimate the reserve account and how to implement it, next step would be to understand which service contract we need to cover the inverter risk, and more importantly, which service contract we need to compare with the reserve account that we just described. In the service offering scope of the inverter manufacturer, we have different components, different parts. One is preventive maintenance. It's not covered by our reserve account. We have the corrective maintenance, labor and material. This is exactly the inverter reserve account that we just described. We have availability, production guarantees, auxiliary services like monitoring. This was not in our reserve account. You can include that in the reserve account, but then you have to put in both sides. The cost of this service in our project is 3,000 euros per megawatt per year. These type of contracts are really complex. So you want to include all the investor needs. We don't have to use the default contract. We at Siconia, we have a good track record on structuring this kind of deals. And we can assure that it is not 24 hours a negotiation. Now, the cash distribution for the long-term service is slightly different than the one for the reserve account. In this case, as the inverter is under warranty, for the first 5 years, there is no cost, and cash flow starts in year 6 with fixed yearly payments, usually until the end of the product life. We had 3,000 euros per megawatt multiplied by 15 years is 45,000 euros. In total, the net present value of this is 24. So once we have explained the two options to cover the inverter risk, let's make a summary and compare them. First one, the reserve account is an estimation. This is important. It's saved in the bank account, but at the end, this is a final inverter cost could be less or could be more. The service agreement, on the other hand, is a fixed cost agreed with the manufacturer by contract. In terms of risk, it's important to understand that when working with a reserve account, the owner accepts all the major inverter risks, while in the service agreement, these risks are transferred to the inverter manufacturer. With a reserve account, the investor has the freedom to change technology, while the service agreement forces him to keep the same inverter for the solar plant lifespan by contract. So we could say that the reserve account option is an inverter replacement strategy, while the service agreement is an inverter repair strategy. Total cost, we've seen before, is quite similar, but the net present value of the reserve account is 35, while the service agreement is 24. It makes sense because the payments for the reserve account are done during the first half of the plant lifespan and the service agreement in the second half. And now the question, which one is the best? Which one is more interesting? To finalize my speech, let me see how to choose between the two options and the things that we must consider when doing an assessment. Investor risk profile. If the investor is a risk-averse or conservative fund, then the natural option would be to transfer the risk to the inverter manufacturer and therefore engage in a service contract. The risk will be reduced and the cash flow will be secure. But if the investor has a short-term strategy, for example, an investment exit on year 10, then the reserve account could work better because a long-term service agreement could work better than a long-term service agreement because the plant owner is not facing the replacement problem. The team is also important. If the asset manager team is not big, the reserve account could be a problem when the inverter replacement project needs to be carried out. This job would be like a new construction project and a new project team setup is needed for it. Again, it's what we called before the cost of opportunity on focusing on a new project or an old project. It's also important to understand the investor portfolio and how diversified it is. For example, if the investor has 20 different inverter brands, even some with string inverters in it, then the service contract negotiation will not be feasible for all of them. And reserve account must be considered for an important part of the portfolio. And finally, the counterpart. It's also very important. The inverter manufacturer. Bankability and long-term plans. This is very important. If the investor is going to sign a long-term service agreement, the other party needs to be bankable enough. And it has to have a clear long-term plan to support the repair strategy. Otherwise, a long-term contract is not a good option. Well, with this, I finish my part. Thank you very much, everyone, for your attention. And I will be available for any questions you may have, probably at the end of the other speech as well.
Indeed. Thank you very much, Francesc, for your insights. Indeed, the questions, the Q&A session will be at the end of also Olivier's presentation, which is coming up. So people, yes, as I said before, please use the chat box for any questions and we will come back in a bit. So our next presenter is Olivier Haldi. He's a business developer for Stäubli in the business unit of photovoltaics and alternative energies, and he's responsible for global key accounts, account management, leading internal projects, and supporting subsidiaries. Olivier, I am unmuting you. Can you hear us?
Yes, I can hear you.
Welcome also.
Thank you.
Give me a second to bring up your presentation. Olivier, I Yeah, I'm now giving you control of the keyboard. You're unmuted, so please go ahead.
Okay. Good. Okay. Well, good afternoon and hello also from my side here at the Stäubli headquarters in Switzerland. And of course, also thank you for joining in today. And also thank you very much to Solarplaza for organizing this webinar and having us. Just also as a short side notice, we are also present at the Solarplaza Asset Management Conferences in Europe, in US and Japan. So this would give us also another opportunity to get in touch with you for some further discussions or exchange. Well, yeah, we know that many investors or project owners, yeah, most of the time don't pay maybe enough attention to also small components such as connectors. So the main goal of my today's presentation is to create more awareness that in quite complex PV systems, also these small details matters, to showcase why also connectors can have a huge impact on the efficiency and the economically success, and at the end of the day that quality, not only on products but also on workmanship and reliability pays off. So before we dive into the topic, let me just share a few words about our company for those who don't know us. So therefore I would like to highlight just 4 of our strengths here. First of all, 125 years of experience. So Stäubli electrical connectors, formerly known as multi-contact, have been part of the Swiss family-owned Stäubli group since 15 years. So this year we also took over the brand actually of Stäubli. Yeah, Stäubli is a technology leader and pioneer in the fields of not only electrical, but also fluid connectors, robotics, and textile machinery since its foundation in 1892. Then original MC4 standard or set standard. So in the growing field of this renewable energies, products from Stäubli have been setting standards, as the first industrial photovoltaic connector, the so-called MC3, was introduced in 1996, followed by then also the original MC4 in 2004. And yeah, setting since then actually the industry standard. Then 170 gigawatt PV capacity. On the slide here, it's still 150. I have to update it. But over 1 billion connectors from our product portfolio have been providing reliable connections all over the world since 1996. So today we have more than 170 gigawatt of installed photovoltaic capacity, which amounting almost 50% of the global cumulative PV capacity. And last but not least, the global presence. We are a multinational group with presence in 25 countries and have agents in 50 countries. So our global or strong global network enables us to provide close contact with our customers through this local support, as for example through our sales and service subsidies. So as mentioned, the aim of the presentation is to explain the relevance of connectors and to underline their importance as a considerable factor for successful investment in the photovoltaic projects. So exemplarily, we want to share some findings here of the independent third-party project or study called Solar Bankability. It's now getting a little bit maybe complicated, but also the entire findings of this project are public on solarbankability.org. So the EU-funded Solar Bankability project aims actually to establish a common practice for professional risk assessment on the basis of existing studies and collected statistical data of failures in PV plants. So its risk analysis tends then to assess the economic impact of technical risks and how this can influence various business models, and at the end of the day, of course, the levelized cost of energy. So the project presents a cost-based failure modes and effects analysis, FMEA, to be then implemented into the PV sector. It tries also to define a methodology for the estimation of economic losses due to planning failures, system downtime, and of course substitution, repair of components with respect then to their impact on the electrical and also financial performance. So to provide then a framework for the calculation of economic impact, a special coefficient called the CPN, cost priority number, has been introduced, and it corresponds actually to the RPN, risk priority number, in the classic FMEA, and is part of a cost-based approach then that has been applied to the collected failure data in order to prioritize the risks and their economic impact by means of the CPN ranking, which you can see here on the right-hand side on this slide. So the Solar Bankability project then applied this methodology to a data set of owner-provided tickets and detected failures during on-site inspections. As mentioned, the methodology is quite complex, but the main message, I think it's clear. So the figure shows that wrong absent cable connections and broken burned connectors can have a big financial impact and are at the top of the list, while also maybe wrong absent cable connectors are possibly more related to poor workmanship and or the use of inadequate equipment and tools during construction. Broken burn connectors are rather than a result of monitoring maintenance issues and also maybe poor product choice during the early stages of the project. So Konstantinos, I think we have our first poll question right here.
Yes, indeed, it's coming up right now, Olivier.
Right.
So yes, the question is, did you expect or know that small components like connectors can play a major role in terms of the efficiency of a PV system? We're gonna keep the question open for one more second. And okay, let's see the results. But I think that a lot of people already know it.
Okay. So maybe we can stop maybe here.
Right, please go on.
All right. So the results of the Solar Bankability project shows that cable and connectors, and as many of you already know, can have a huge impact on the yield of this PV plant. But the question is, of course, now, why do connectors have such impact on the overall yield, and is there also an economically feasible way to reduce these risks? So connectors are actually used in PV systems to ensure constant transmission of the generated power from the models by connecting them to strings, combiner boxes, and inverters. Yeah, they are used in large numbers. For instance, in a 20 megawatts solar park, depending, of course, on the design. But we have around 140,000 connectors installed. So the key to efficient operation and energy feed-in is long-term reliability related to cabling and connectors on a constantly low contact resistance. So vice versa, can say an increasing contact resistance inside the connectors induce higher temperatures and power loss, which then increases the contact resistance again, creating a kind of a spiral resulting in high risk of partial connector failure. So the consequences caused by the increasing contact resistance of these failures leads to lost power due to downtime, expenditure on service hours, costs for spare parts and reconstruction measures, and maybe also, in the worst case, to legal costs. So depending on which connector or connectors are affected, only one module or maybe also an entire string of a PV plant is disconnected. This does not disable the entire plant, but will lower the overall yield, of course. So the detection also of the faulty connectors may then turn out to be a difficult task. Chances are low to detect the bad connection if a central inverter without string monitoring is used. And even if it is detected, qualified staff needs to be dispatched in order to track down the exact location and to fix the issue. So now let's have also a look on the big picture. The construction and the operation period or phase of a PV system. So it's in this context, it's interesting to know that these components for cabling comprise only around about 1%, and for connectors only around about 0.003% of the total overall total initial costs, so the capex of a PV system. And also then of course price savings among these component choices are roughly more than, let's say in this example here, 30%. So therefore it is appropriate, I think, also to ask if the savings of only, in this example, of 0.001% of the total initial costs gained by maybe using cheaper components is justified when considering the additional safety risks during operation and decreased efficiency on the or return on investment such a choice then might bring. So the findings of the Solar Bankability project gives a kind of a indication of the economic risk of these failures, but for any single project, they are, of course, depending on a lot of different factors and can't be really calculated in detail. Nevertheless, it's obvious the usage maybe of low quality connectors involves many risks and can have, as also pointed up by the CPN, cost priority number, an impact on the return on investment. So when we break it down also on the levelized cost of energy, We know today it's all about balancing the capex and the opex, and then optimized energy yields. So, of course, the involved project stakeholders might have a slightly different view with different intentions on this. So, in order to lower the capex, one may try to lower also the costs of cabling and choose low quality products, or maybe also cheap workmanship. But as already shown, we can see the potential for optimizing the capex on these components using low quality connectors is very low on one side, but at the same time, failures of caused by the small components can have a not too minor negative impact on the OPEX, and also lower the energy yield. We have learned also that the key factor of operational efficiency is, in this context, a constant low contact resistance over the years. But what can cause, or what can be the root for an increase in contact resistance? So not only the selection of quality components, but also their correct handling are crucial for the system's profitability. So we see mainly three sources of risk which can lead then to the mentioned consequences, and puts the need function at risk. First of all, of course, it's quality, performance, and the long-term reliability of a product. Secondly, the cross connection, or also known as cross-matting in the industry. And last but not least, defective installation, or also crimping. So pay attention to these topics. We think is key to mitigate this risk and failures detected or pointed out also by the Solar Bankability project. So product quality, first source of risk. This illustration here, for instance, shows the result of a standard norm testing, damp temperature cycle test 400 and damp heat test 1000. So every connector have of course different contact technology, dimensions, product material, product processes, etc. However, some very similar rules which are applied actually also to the PV model manufacturer can also be applied to manufacturers of other components, and the edge that you get what you pay for. So the quality connector, here as an example, our connector is also almost totally stable. This is the green curve here in terms of contact resistance, but also you see the temperature in the picture. So the use of low quality connectors is also shown by this graphic here, is risky, as the strongly increasing contact resistance curve here illustrates, and also the picture of the thermal camera. So it's almost impossible to foresee by when an increase in contact resistance then will lead to a connector failure. Could be at day one after a connection, but also after 5, 6, or 8 years. But sooner or later, it can lead to the mentioned consequences you also can see here again on this slide. So sometimes it's maybe also not enough when a product is certified and you just have a quick look on the related data sheet to check the performance of a product. So additionally, data on a long-term performance can be really helpful also to indicate the real quality. Here on this slide, we have another example of an internal beyond the norm testing, 10,000 cycles, which represents around about 20 years of our product, showing a stable contact resistance. So, and what is also interesting is to know that additionally to the resistance of the contact parts, there is a resistance of the crimping, actually the connection of the contact parts to the cable. This beyond the norm testings and in general, data from laboratory is of course helpful to assess the quality, the performance of a product. But sometimes it's maybe not enough when a product is. We have here also real field data, which is maybe in this context also even more significant. You can see also a figure of a rooftop PV system. So the curve, the values proves also the constantly low contact resistance over years. In this example, over 12 years. So second topic or risk source, the already mentioned cross connection or cross matting. Means choosing reliable product is only step one, but that's not enough then. There are no established standards for connector technology in the field of PV, but a quasi standard is set with the connection type MC4 from us, from Stäubli, or multi-contact. And we see in the market a lot of MC4 compatible or pluggable, MC4 connectable, but connectors of particular manufacturer have their individual plug-in phase, the exact specifications, different technology inside, different material composition, production processes. So if connectors from different manufacturers are combined with another, the connection might not be secure. In fact, also cross connections are one of the most common and cost intensive source of failure in PV projects. So cross mating of these connectors can cause cracks, leakage, and increased contact resistance of the system, which also this figure here on this slide demonstrates quite well. Cross connection, however, is not permitted under any circumstances, and may lead, as mentioned, to also the consequences before. So therefore, it's absolutely important to pay attention to use the same components during the whole installation process. And what is also interesting here, you see another example on the left-hand side, cross connection versus the original on the right-hand side. So by mismatching or cross-connecting, you're easily creating a source of risk, not only technically, but maybe also on a legal point of view. So there is no compatibility and no certification for a cross connection because of the product norms mentioned here also. So that means that two cross-connected connectors will actually lose their certification. Then, last but not least, third source of risk is correct installation of the whole cabling, of course. But here we have to focus on the so-called crimping, which is actually the connection of the connector with the cable. So for correct crimping, also a certified crimping tool must be used, which is suited for the particular type of connector. And usually the installer plugs the connectors in the field. So it's absolutely crucial here also to work with a well experienced and trained EPC or installer, and inadequate or the adequate tool is in use. So crimping with a non-certified tool or just with a plier is really critical. So is maybe not fulfilling the norm criteria. You will have no stable contact resistance, no gas tightness. And also this figure here shows again contact resistance curves of the different crimping connection and the increasing contact resistance, which then also can lead to the already mentioned consequences. So to sum up, on one side we have small components with a very low portion of the total costs, a little financial weight, but at the same time the potential savings is very low. And on the other side, we have learned that these connectors can have an impact on the efficiency, safety, the economically success of a PV system. So here also, quality matters for these components. And of course, the project owner has to weigh the cost for construction and operation with the goal of optimal performance of the system with the minimization of the levelized cost of energy. But to mitigate this risk failures and maximize the return in the long term, we really recommend to pay attention also on cabling and mainly on the mentioned related three main risks: quality of the product, quality of the installation, means preventing cross connection, and the defective installation or crimping. Well, thank you very much. That's it so far from my side.
Thank you very much, Olivier, for your presentation. Indeed, small components, but with quite big impact. We missed actually one of the poll questions, so just for a second, let's also go through this one. So the question is, have you been aware of the non-compatibility of different connector brands? And okay, we will close the question, and the answer is actually the indication for you.
Yeah, almost 50-50.
Almost 50-50, exactly. All right, thank you very much, Olivier. So we can move on to the Q&A session. So the first question would be addressed to Francesc. Let me unmute you also. So Francesc, the inverter replacement is forecasted in year number 10 after the installations. Is this a little bit optimistic? And the comment is that in Italy, the replacement market is growing year after year, even if we are only at the 6th-7th year after the installation, at least looking towards the major portfolios installed. What do you think about this, Francesc? Francesc probably cannot hear us.
Can you hear me?
Yes, now we can.
I was saying that yes, in fact, it was a very good question, and in fact, there is inverter replacement in years 5, year 6, year 4. So inverters becoming obsolete before we expected. It's true. We will also have the case that inverters becoming obsolete in year 13 or 14. So yes, I took a very theoretic number to make the simulation, but I agree that we could have specific cases when the inverter becomes obsolete before year 10, indeed.
All right. Thank you. Another question for you. It's more of a comment, actually. So Jan Bresinski is saying that according to their experience with a leading German inverter manufacturer is that without a penalty agreement or penalty agreements, a full service contract worth nothing. What is your take for that?
I think that in general, contracts and warranties are worth the company that is signing this contract. So if a contract is worth nothing, it's because at the other side we have either not a properly written contract or not a bankable company. But if we agree with a bankable company with a properly prepared contract, we agree supply of spare parts and labor, and this is a contract. This contract is as valid as the O&M contract or the EPC contract or the insurance contract. So we need to work on the contract and we need to work on the counterpart to make it have some value.
Makes sense. Thank you. What about preventing maintenance or the availability guarantee? Why are these not covered by the reserve account?
Good question. In our case, we consider them to be out because they are not covering these risks, let's say, directly, especially the obsolescence risk. But yeah, I would agree in a scenario where we consider them in both sides. So we just see higher prices for this comparison. But yeah, we could include it was an exercise, and what we were focusing, don't forget, we were focusing in the obsolescence, which is the major risk. And preventive maintenance at the end can be done by the O&M operator. The availability can be also included in the operator availability, but it's something that the O&M operator will never cover. That is the obsolescence of the inverter after year 10. So my exercise was focusing on covering this risk. But yes, we could include them and do another presentation in a few days if you want.
Let's do it every day. All right, thank you, Francesc. Let's move on to Olivier. Olivier, what are the main criteria which a project owner should consider by selecting connectors?
Well, yeah, of course, it should be done in the planning or construction period of a PV system, and we would recommend not only to check if the product is certified and check the data sheet to the product. So it is also related to is it a bankable partner? What is the track record? The data from the field, the experience. Maybe they have also beyond the norm testings, with whom they are working, which partners. Is there also, but around the product, kind of expertise and support, local support. For big customers, maybe it also makes sense to have an assessment or an audit of the supplier.
All right, thank you. Makes sense. Also, again, question for you, Olivier. How can a plant owner or an O&M company detect failed connectors in the system? Or are there any preventive actions, strategies that you would recommend?
Yeah, I would say also this is maybe a little bit depending on, first of all, the design of the system and but also maybe on the O&M contract. So checking the cabling if it's correctly done, starting by junction boxes with the whole cabling, of course, the connectors. If there is no cross connection in the system, maybe also together with the installer or the EPC. And the other then topic is, of course, monitoring. As already mentioned, it's also depending on design. So you can do it maybe via the inverters or power optimizers, but also a visual inspection. We would recommend maybe also with, for instance, a thermal camera to detect also the hotspots, which then, I'd assume that there we have an increasing contact resistance.
All right, thank you very much, Olivier. Francesc, coming back to you, too many major inverter companies have gone out of business. So a lot of parks, I guess, are too dependent on one inverter company. Is this too high of risk that is not presented in your strategies?
Yes, it's a very good question again. Your audience is really good. In the last slide, actually, at the end of the presentation, my last words were inverter manufacturer bankability and long-term plans are very important. So when trying to transfer the obsolescence risk, the most important part is to do a due diligence on the counterpart of this contract. So the major risk is exactly that. The other part is going bankrupt, and the question went to the point. We need to assess the inverter manufacturer, and the major issue is that.
All right. Another question for you, Francesc. For the reserve account, why should it be collected within the first 10 years? So if we collect it between the years 6 to 10, then the NPV will be closer to the other option that you presented, the long-term agreement. What is your opinion on this?
Yes, this is not our decision. This is usually established usually by the bank or the lender or the technical advisors. This is industry standard, actually. So probably, yes, there will be other ways to set up, but in general, I would say that 80–90% of the reserve accounts are configured this way. It's an industry standard, and maybe nobody thought about that and just put 10% during 10 years, but it's the more established way to set it up.
All right. Then how about, according to your experience, is a high-grade qualification of an inverter, does this help investors and buyers on choosing inverters? And by high-grade, Marco means qualification based on climate zone where the inverter is installed.
Yes, at the end, the quality and the product and the features of the product will help reliability. But it's very important to understand that the obsolescence has to do with the breaking the chain with the supplier. So you can have the best quality product, but if one of the suppliers of one of the components is just not supplying this component anymore, the inverter becomes obsolete. And you can have the best inverter in the world working perfectly in very extreme conditions. But when you need to replace the component, it's not there. So obsolescence is more than quality. It's making sure that you have all the components and ready to repair the inverter when it's broken.
Indeed, and it's something that we have seen in the past years in this new industry of solar. I think we're going to see more of this in the future. So let's see. All right, gentlemen, Francesc and Olivier, thank you very much for your time and your presentations. we don't have any more time to continue. There are a couple of questions, but we will just forward them to you. On behalf of Solarplaza, thank you very much, all the attendees and the presenters. If there are any questions, you can just contact either me or my colleague Elko. We're both working on our next conference coming up in Milan on the 7th and 8th of November. As I said before, it is the biggest conference on the operational phase of solar PV assets in Europe. And of course, the next conference from the solar asset management group of Solarplaza is going to be in San Francisco in the USA in March 2018. So thank you very much, and have a nice afternoon and evening, all of you.
Thank you. Bye-bye.
Thank you. Bye-bye.